to our speaker today, and that is Ben Traynor. Actually, it's a great honor for me to to introduce Benjamin Traynor-Schloss, who joined Google in 2003. Well, that's been a while, Benjamin.
More than one.
To lead the Google's nascent site reliability team at the time. He led the development and operations of Google's network data centers and production software infrastructure, and operations for Google's internal and user-facing services. He invented the role and term site reliability engineering as a distinct discipline that efficiently creates, supports, monitors, and improves the availability and performance of large software systems and services. In 2025, Ben was promoted to the role of Chief Programs Officer at Google, leading multi-year Google-wide efforts, including data center efficiency, AI diffusion, infrastructure capital structures, and long-term capacity and supply assurance. Ben started his career as a software engineer at Oracle at age 17 and has worked in a number of leading-edge software companies. So we're really delighted to have Ben join us. Again, one of our own at Google. So with that, I am going to hand it over to Ben so that he can educate us on all of those really, exciting things when it comes to the gigawatt scale infrastructure that you've been working on, you and the team have been working on. So over to you, Ben.
Great. Thank you so much for the introduction. I'm going to attempt the risky technical move of taking over presenting here so that I can actually use the arrow keys. So bear with me for just a moment. We'll see if this works. This. And yes, it's okay that it's being recorded. And I'm ready to present. And here we go. All right. It appears the system works.
Yes, it works.
Excellent. All right. So I'm here to talk to you today about ML in the gigawatt era. And I will preface this, as you noted, by saying my whole background is software engineering. So I've often approached some of these scale problems, whether they're infrastructure or systems or operations, through the lens of someone who considers himself still a software engineer. But there are a lot of bits of doing very, very large scale ML deployment that actually look like software engineering problems, or more generally just engineering problems. So expect a bit of that lens throughout this presentation. Where are we? Well, I wrote this 3 months ago, but it's still basically true. As of this writing, deployments of machine learning at 100 megawatts, right, 0.1 gigawatts, this is pretty routine, right? All of the large AI labs are operating at this scale. A number of non-AI labs are also operating at this scale. I would call this, whether it's deployment or operation or lifecycle management, this is now GA, right? So far, so good. The problem is 1 gigawatt deployments are not GA. They're not even really pilot at this point. They are in proof of concept in many ways. And there are a lot of things that crop up as you go from 100 megawatt to 1 gigawatt deployments that actually has to change. And so a lot of this presentation, we're going to sort of get into what those are and then some solutions for them. But it's interesting to put this in context, because if you were to read the press right now, you would say, well, what is this guy talking about, right? Everybody's doing gigawatt scale deployments. I keep reading about 100 gigawatt scale deployments. The actual number of 1 gigawatt ML campus deployments right now in the world is an order of magnitude smaller than the number of functioning fusion reactors in the world, right? I think at the time I wrote this, there were fewer than 10 in the world, and they were all in the process of being either spun up or further developed. So this is not at all common or routine. It is novel. And as people are discovering, right, as you start trying to build and then deploy at this scale, basically everything has to change. We actually have a lemma internally at Google, which is that, with every order of magnitude increase, you have to redo everything. And unfortunately for ML and ML deployment, that is proving to be true once again. So credit to Jeff Dean for having pointed out that this was likely. So let's talk about what needs to happen. So first of all, if you're going to do a gigawatt scale ML, you need to do planning and construction differently. The data centers don't work the same way, and the data center planning doesn't work the same way. You need to do deployment differently for reasons we'll get into, but essentially if you wanted to deploy a generation of a given type of ML, you cannot do it in the same way that you would deploy 100 megawatts of that ML. The network is totally different, and it is for a couple of different reasons, but mainly because of some of the implications from planning and construction and deployment, but also because the uncertainty or error bars around planning for network flows go into the scale where they collide with the realities of current network transmission technologies. Server life cycles also have to be treated differently at this scale. You can't sort of use the same approach of life cycle management for these servers. And since they're very expensive, and there's a large number of them, actually this life cycle becomes really critical. And then finally, reliability, a personal favorite topic of mine, but also a really critical topic when it comes to either doing training or doing inference and serving, is very different at a gigawatt than it is at 100 megawatts, and multiple gigawatts just gets even more challenging. So we're going to get into all of these topics as we go through this presentation. Let's just take it from the top. All right, so historically, right, how do you do data center planning and construction? Well, you would decide where you wanted to get your data center, either because you had land or because you had power or both. You would hire a firm, they would design and build the data center. You would then fill the data center full of ML. There is something in there about a sustainable business model using ML that will be a topic of a different talk, but not this one. And then profit and life is good, right? And typically, one of the things that you discover as you get into this is that the construction speed and parallelism that you can have in a given campus is a function of available labor as much as anything else in the region, as well as, of course, materials and materials flow. And as you do these projects, and let's say, for the sake of argument, I built order of magnitude 10 gigawatts of data center capacity here at Google, what you discover, you can build 100 megawatts a quarter, maybe some campuses 200 megawatts a quarter, but that's kind of it, right? If you try to go beyond that, there isn't enough space, there aren't enough people in the different trades, it's hard to get materials, even concrete, right? And so this is sort of the upper limit of what you can do in terms of throughput. And so once you discover that, of course, you can kind of see where this is going, which is to build a 1 gigawatt data center campus is a problem, right? If you're doing, let's just say for the sake of argument that you're doing that at the 200 megawatt a quarter throughput rate, which is like as good as you're going to get, right? Okay, well, gigawatt scale then being done that way takes 5 quarters from start to finish, right? First data hall comes online through last data hall comes online. Little problem. Machine learning servers go through a generation change more quickly than that. So what we've just discovered, right, through this paper exercise is that actually by the time you're finished building that 1 gigawatt campus, you don't even have the same server type that you started that campus with. You have multiple generations in the campus. And for those who do training at scale, that's actually not good because training often requires a homogeneous set of participating servers for it. Plus you have the other problem, which is because you're building this thing over the course of what essentially is a year and a quarter to a year and a half, you have hundreds and hundreds of megawatts of capacity sitting idle. If you try to populate the buildings, then you have these machines there that are not actually at their full scale and can't do the mission they were intended for. If you don't populate them, well, then you have a ton of very expensive empty data center space there, along with the associated power contracts, consuming interest. And so all of these are basically challenges that you get because you cannot sort of will a 1 gigawatt data center campus into being in a quarter or two. And the torrid pace of server development challenges this rate of data center build. So what do we do about this? Well, basically you go parallel, right? The degree of irony in its parallels to how machine learning works noted. But you basically build gigawatt scale over multiple campuses so that the time required to get an increment of capacity for your next generation is reduced from 1.5 years to, let's say 6 months, right? 6 months is small enough that you can fit a single generation of ML in there, blah, blah, blah. And you can get this scale that you want. It also lets you deploy the servers themselves, which we'll get to in a minute, but it lets you get those deployed in a parallel fashion so you can get much higher throughput to these different places. Now, there's a problem with this approach, which is probably obvious to those of you who have ever played with networks, which is these are not all in the same building or the same campus. So suddenly you've got a wide area network if you want these different sites to participate, right? If you've got a gigawatt, but it's in 3 or 4 locations, then you've got a bunch of WAN network to build, and we'll get into that in a second. There is another problem, which is what I call nature abhors a vacuum, right? If you're building these large campuses, it's very difficult in practical terms to keep the whole company focused on using them for the purpose that they were intended across all of the campuses, because everybody sees this space coming online, and as has been the case for a long time, demand exceeds supply. So all sorts of different teams and uses pop up to say, well, can't we get part of this capacity for our own use? And so this actually points you back to the faster you can get all the capacity up and running, the better. And the faster you can deploy the servers into it, the better. But it has to happen in months if you really want to have a large scale ML deployment. All right, so let's talk about that ML deployment, because it is actually not a small problem. So again, back to our historical approach. Historically, you would build a 100 megawatt data center. You would fill it up gradually over the period of 1 to 3 years as your demand emerged. And even if you were filling it up, let's say, over a short period of time, you still had a peak of like 12 minutes per rack to deploy things. And the math is maybe interesting to look at, but you say basically 100 megawatt data center, 1 rack is 15 kilowatts, so that's 6,700 racks per data center. There's 250 working days a year, which means on average, you're gonna put 25 racks in that data center per working day, give or take. 2 to 1 peak to average, so you kind of need to have enough throughput to do 50 racks a day, and therefore that's maximum throughput of 12 minutes a rack over a 10-hour day. So life is not good. This is hard, right? 12 minutes a rack is a lot when you typically have 1 or 2 security paths to get onto the data center floor, but it is doable with some coordination and work and practice. However, right? If you're trying to build one of these gigawatt scale training or capacity deployments, even if you split it up into several campuses, right? 5, you still now are building a data center that's twice as big, and you have to fill the whole thing in months, not 3 years, not even 1 year, right? And so here again, the math, right? For the sake of making this seem vaguely tractable, I assume now we're talking about ML, so it's 30 kilowatts rather than 15 kilowatts a rack, still 6,700 racks, still same number of working days, but you need to fill it in 2 months, right? In order to have your capacity all come up and be useful and not have a ton of area under the curve where you're wasting tens of billions of dollars of available capacity. And so now you have 320 racks a day for a given data center. And that is actually extremely hard. That's a rack every 2 minutes. And you have to be able to do that routinely at 5 different campuses all at the same time. And this affects everything. It affects your staging areas, your loading docks, your security, your materials path, your staffing. For those who deal with staffing, you also have this problem of you have an enormous need for people who are highly skilled and capable of moving racks and deploying systems for a very brief period of time, and then you don't need anything like that number again for 5 years. And so this is a huge staffing challenge, in addition to sort of the logistics and technical challenges that we've just described. But this is what's required if you do this at 5 campuses. Obviously, if you do this at 1 campus, somehow or another, it gets 5 times as bad. But this is exactly the problem of a gigawatt scale deployment. All right, so earlier I mentioned that network is also an issue. And again, if we talk about sort of the traditional way that this works, you have 100 megawatts, it's in a single building, you have a data center level LAN network, and although the size of that network is large and it's uncertain because the practice of doing machine learning, training, et cetera, is evolving rapidly, it's still a LAN network. So we all know how to horizontally scale a LAN network. Life is relatively good. But with gigascale, right, now you've got 5 campuses. You have WAN. WAN requires a whole different kind of engagement, physical planning, permitting, trenching, right, rights of way, land acquisition, blah, blah, blah. So you have to plan LAN or WAN network years in advance. And you then run into this problem, which is no one knows how much network will be required for machine learning use cases 2 years out, right? If you ask any team, and it's not because they don't care or because they're not competent, it's because this is an R&D topic, right? And so the answer is we legitimately don't know. We think maybe it might be this upper bound that's always petabits, right? But we legitimately don't know. And yet somehow you need to plan and permit and acquire enough equipment to construct a really, really big WAN network to cover off your upper end. And you need to do that before you really have even approximately correct information about what the total demand is. So then you need to run a lot of conduit, you need to run a lot of fiber, and then you basically late bind all of your expensive choices like transponders and et cetera, et cetera. But this is a very, very different kind of problem for networking than it is when you're just dealing with a single building's worth. So here, what do you do? Well, there's a couple of bits that help us here. The first is that network capacity is not binary, right? It's not like if you don't have the ideal amount of network bandwidth, your whole gigawatt scale deployment doesn't work. It's rather that it is inefficient, right? And you know, the way most training works, you do a bunch of compute locally, and then you exchange information with all the other participating nodes, and then you go back and do another round, and sometimes that exchange is continuous, and sometimes it's discrete and step function. But either way, the network bandwidth that you have available between different participating nodes in training affects the overall throughput, or what we'll call goodput, of that combined set of deployment. And there is actually a fairly straightforward way, once you know how the training is going to work, of computing how much more goodput you get by adding network versus you know, how much more cost you bear. If you assume a fixed budget, then you can actually say, well, no, we're now optimizing this value function, because if I'm spending money on network, then I'm not spending money on data center and server. And so I can try to pick the right amount of WAN network so that I'll get the most goodput for my capital dollar. Again, harder to do because of the uncertainty that we just discussed, but that's life, right? When you're planning these data centers, you also don't know exactly how much capacity you'll need either, because no one's certain about the power draw under different workloads, right, at the 1 to 2 years out. So all of these are essentially modeling problems under the face of uncertainty. And essentially what you get to is you use news vendor to decide how much WAN to plan to build based on your expected loss of throughput if you build too little network and the the training pods wait for transmission, versus if you spend too much money on network and you end up having less compute power as a result of having spent your capital budget elsewhere. Anyway, this is part of the fun of planning. And again, Gigawatt is, I think, using publicly available data. Let's call it comfortably $40 to $50 billion. The numbers here are very real, and it's actually very, very valuable to be able to do these calculations as precisely as possible. So a lot of thought goes into this. But this is the basic problem as soon as you get to multiple campuses. All right, so let's talk server life cycle, because this is another issue, right? Here we have, well, 4 AI renditions of what different generations of ML looks like, but bear with me. I think the last one is probably still in the lab stage, I hope. But the ML hardware, as we talked about earlier, is evolving incredibly quickly. And the hardware that 2 years ago was cutting edge, everybody's going to build their next frontier model, these days is well, how can we use it to run our medium to large serving models on, but we're not going to actually do frontline training on it. And so the ML hardware is evolving faster than the data center capacity. It's really much faster than sort of we've seen since the early days of Moore's law. And so you have to think then about how do we deal with the servers not over their first year, right, when they're all deployed and networked together and so on, but then over the other 5 years of their economic lifespan when you still need them and you still spent a bunch of money on them. There's a further problem actually when we get to this life cycle, which is, as we talked about earlier, the ideal deployment for ML would be all in one giant building because you get it all close together and low latency and cheap network and blah, blah, blah. But we can't do that for practical reasons. So we spread it out amongst a small number of campuses that are as close to each other as you can arrange. This is optimal for the training use case. It's also pretty much pessimal for the inference case, because now all of your capacity is in a small number of locations, each of which could have a failure, and the SLO required for inference is 2 orders of magnitude higher than the SLO required for training. So what you really would like is to have all of this capacity that you built 1 or 2 years ago now redistributed around the globe so it can be close to the user and low latency, and your failure zones are smaller so you don't need as much redundancy and so on and so forth. And this is I would say, a currently unsolved problem, although there's some obvious and some non-obvious approaches. But what I would say generally as you're sort of working through this is you have to plan for a generation change every couple of years here. And you have to answer the question both, what am I going to do with this capacity once it's not being used for frontline training anymore, and I want to have it more geographically distributed, but also what am I going to do when its power draw changes, because instead of being run for training, which is a very, very high draw coordinated behavior amongst many servers, now it's being used for inference, which has typically a lower power draw, but also a non-coordinated behavior amongst the many different servers. And if you don't plan this correctly, again, $50 billion a gigawatt, there will be regret. So a bunch of potential solutions. One of them is, well, maybe make your campuses big enough that they can host several generations, and you just keep building data center. And whether or not that makes sense for your work and your particular application is a model that I guarantee you is worth running carefully for yourself. All right. Finally, reliability. Like I said, one of my favorite topics. So the big challenge is that a training exercise essentially requires that all of the participating nodes are working, because they all have a small piece of the problem, and they're all basically doing computation and then exchanging data and so on. And so if you lose a node during part of a training run, you need to restart that training run typically. And that immediately takes you down the direction of, well, okay, so we need to have checkpointing so that when we restart, it isn't, like we lose a day's work, but rather we lose an hour's work or maybe a few minutes worth of work. But you also have this problem of, as the training scale gets bigger, you're still stuck with individual node availability affecting the whole training pod. And so what you actually discover pretty quickly is that the impact of node reliability scales as n squared with the size of the training pod. And so it becomes very, very important that you have highly reliable nodes in your training pool, and not just nodes, but also network and rack and power and everything else, in order to be able to do large scale training. And even a small change in individual node availability over a much larger number now has this profound effect. Once again, the idea here eventually is you need to compute Goodput, because for training in particular, it's a batch process. So what you really care about is how long does it take for all of these nodes together to produce the trained output that I want. And you have to then sort of consider node availability and network availability, as well as scale. And what you actually can find and will find is that as you look for a particular level of availability, there's a max size cluster, right? And as you're adding more capacity to that cluster, your Goodput's barely increasing because of the the impact of availability. And at some point it noses over. Actually, you add more capacity to a cluster and it gets slower because the cost of the additional unreliability that's introduced with that additional capacity outweighs the throughput improvement that you get when everything happens to be working together. And you also have then these problems of needing to do checkpointing, which requires fast storage, and back to my earlier topic, a lot of fast networks so that everybody can checkpoint together. But this is another one of those modeling problems where it's really, really critical that you actually work through the particulars for your own application, because again, $50 billion a gigawatt, right? A lot of motivation there. And so as I was saying, right, a Goodput model here, it has to look at scale, node availability, checkpoint time, checkpoint frequency, and available network bandwidth, and obviously changes that you can make to how training is done or how synchronization is done can have a very profound impact on the overall Goodput of your hardware. And back to that $50 billion thing, it's very much worth throwing engineering at this problem, because at 100 megawatts, it's already expensive, but at a gigawatt, it's eye-wateringly expensive. And so the improvements that you get from engineering solutions, including software engineering, become quite a bit more valuable with this increased scale. The other sort of obvious takeaway is that node reliability is incredibly important, right? If you can decrease the failure rate for your individual nodes, you can have a profound impact on the Goodput of a given size deployment, and that again is worth a large amount of money. So people do talk about sort of the overall scale of these systems, but what we actually care about really is the overall Goodput of these systems, and that's the thing that both your your researchers and your user base will ultimately care about. All right, so in conclusion, I wanted to leave some time for Q&A because there's always some interesting topics there. When I first got asked to talk about gigawatt scale ML deployment, I was sort of like, yeah, that's a really interesting topic, but how am I going to find enough content in here to create 40 minutes worth of interesting? And as I went through it, what I actually found was there were so many different things that were worth talking about, and the value of this, because of the enormous cost, is so high that I was paring down. But it's a fascinating topic. I would say the one bit that, if I can impress on you nothing else, modeling out what your Goodput is going to be for a given deployment is absolutely critical, and you have the opportunity to make really profoundly large differences in outcomes by doing some careful modeling and planning with these larger scale deployments. A 2% improvement is $1 billion, right, per generation. So please, let me exhort you to use engineering, use modeling, but carefully plan out these large scale deployments and plan out how you're going to use them and how they scale, and et cetera, and you will be worlds ahead when it comes time to actually put money into the ground. With that, I am done with the presentation, so let me hand it back over, and I will be interested in the questions.
All right. Thank you very much, Ben. That was wonderful. It was
30-minute
you
monologue.
know, it's amazing, um, the scale at which you're operating at. And so there was one of the questions I saw in the comments. So let me go to that one first. And I have a question somewhat related to that. But yeah, the question is, you know, and I've built large computer systems as well, and reliability and the failure of individual components and the MTBF becomes a concern. Now you're talking about like several orders of magnitude more than that. What is your philosophy? How do you go about sort of creating a system that's resilient, that stands up, as components fail and so on?
I mean, as you know, there's no magic to this, right? Essentially, there's three things you can do. Thing number one, you can make the cost of failure lower, right? So if you can change the impact of a failure from all of your nodes need to restart to some of your nodes need to restart, or even only the local rack needs to restart, right? And run the computation, that has a profound impact. Haven't seen it done very well in practice yet, but again, ML is very much an R&D topic right now. And as these scales get larger, the value of that particular topic is going to go through the roof. The second is actually improve your node availability. And this, I work at Google, so I will take a moment here. This is actually a place where we've spent a lot of time and effort with our own hardware because, of course, we are our own customer number one for the hardware, and all the people over in DeepMind are very smart as well. They understand this dynamic. But so having very, very reliable individual nodes, having very reliable node interconnect so that the system of a rack or 4 racks working together is itself highly dependable. Has a profound impact. And then the third really is to have very, very fast recovery time, right? So, if your failures are relatively frequent, but it takes you 5 seconds to recover from failure, then the overall impact on Goodput is not actually that bad, right? If it takes you 30 minutes, because whatever you're checkpointing once an hour, then it's very, very costly. Right. And so this gets back to that balance of how much network do I build, right? More network means faster checkpoints, means et cetera, et cetera, et cetera. But of course, it also means less money for the hardware. But any and all of these are fair game. And they're all sort of places that I see everybody pushing on because, again, the dollar figures are so very large.
Okay. All right. So we have a question that's come in. Let me read it. I think it's somewhat related to reliability, but you mentioned reliability as part of the design process for gigawatt-scale data centers. With your SRE hat on, how much has changed with this advent of required power? Are things more complicated or more or less power for the cores?
The advent of, you said required power or?
Of required power, yeah. So I guess, you're not talking about hundreds of megawatts, you're talking about gigawatts.
Yes. So interestingly, data center availability is much less important than you would think in this. And why? Well, because as I said, the node failure knocks the whole system back to its previous checkpoint, right? That's sort of the normal way things work. So it doesn't really matter whether one node fails or 20,000 nodes fail, right? And data centers therefore don't need to be as reliable for training anyway, as you would expect or as you would normally want, for example, for an enterprise use case, because the impact of, let's say, 3.5 nines or even 3 nines data center availability on overall Goodput is actually quite modest. The Goodput is dominated by this individual node failure. And so that opens up a very interesting opportunity to say, well, all right, so if the data centers don't need to be quite as available or reliable as they used to, maybe they can be connected to somewhat less reliable power, right? And there's a really interesting study done by Duke University in the last year that sort of looks at the US grid alone and concluded there's something like 100 gigawatts, really, of available power in the US grid if we could relax the reliability or availability of the power demand, right? And so this is a really interesting sort of opportunity that I can talk about because we've now said some things publicly. But it is, it is another place where data center and data center power connection topics get to be rethought in the face of these large scale planning and deployment.
Okay.
So hopefully that's the question that was being asked.
Well, Brian, if you'd like to clarify, feel free to add another question to that. So, we all, given the challenges, and you talked about checkpointing and things like that, how much are you relying on software-defined resiliency at the end of the day, right? Are there any other techniques that you use that are maybe, the end user is not aware of? Like, do you do like intelligent rerouting and all of that stuff?
Well, yes, for sure. I think so. There's a lot of sort of traditional availability practices that come into play with machine learning, and I think we do have to differentiate between the training style workloads and the interactive or inference style workloads, right? For training workloads, the key thing to remember is it's a batch process, right? Nobody actually cares how many megawatts you have. I mean, the press department maybe, right? And the investors maybe, but nobody actually cares about how many megawatts you have. They care how long it takes to do an interesting training job, right? And so whether you do that with 100% of the capacity running at 100% of the time, or 101% of the capacity, right, running at whatever that is, 99.05% of the time, no one actually cares, right? They just want to get their job done. And so this opportunity then gives you all sorts of options for both software, but also, frankly, hardware choices in the data center, in the network, right? To let you get this capacity online. And so all of those techniques then crop up. For inference, a lot of the standard SRE stuff comes into play, right? You need to have redundancy and the users notice if you have a failure rate that is different from what they would expect from the underlying access, right? If you're using a phone, people need 2 nines of availability. If it's a big enterprise application, it's 4 nines, et cetera, et cetera. But one of the key differences with inference, at least so far, is it's slow, right? Like you're not getting the 150 millisecond web search query response or, pick your poison, right? A 2-second Gmail delivery of some file with attachment that people have gotten used to. Inference, often you type the query and then there is this pause before you get anything back. And so that means that you don't have to worry as much about speed of light between where you're serving inference from and where the user actually is. That's a very small fraction of the total latency budget that your service is dealing with. And that gives you the opportunity then to deploy inference capacity in more concentrated, geographically concentrated ways than you would some of these low latency products. Obviously, you still need to then worry about availability, and if you deploy everything in one place, well, you can't have good availability, so you need to deploy it in multiple places so that one of them doesn't work, your service doesn't all go down, and that becomes a trade-off between sort of fixed cost and availability and scale. But all of these topics are there. You have extra degrees of freedom because you have a massive relaxation of the latency requirement.
Right. Okay. 2 more questions from me, again, both related to the infrastructure and the hardware. One is networking. We've seen InfiniBand really take center stage when it comes to AI training and to some extent inferencing as well. And we're seeing more and more optical. What is your sort of view? Like, where do we go from here?
I mean, that's kind of the fun of AI, right? We're finding out. If any of us knew exactly where things were going, or which approach would end up being the dominant or superior approach, we would be worlds ahead. But everybody is essentially experimenting and trying things right now. I think, some of the physics problems that I just described are only going to get worse as the scale goes up, right? I here have talked about what happens when you try to deploy 1 gigawatt, and I made the point,
Right.
which is true, that is the current cutting edge, but that won't be the cutting edge in 3 years if things continue on anything like their current trajectory, right? It's going to be 5 gigawatt deployments. And all of the same things I said about campus construction are going to be true. So now you won't have 5 campuses, you're going to have, unfortunately, probably 30 campuses, right? And so then you have to say, well, okay, InfiniBand sounds great, but what about the WAN problem, right? Like what you just told me is, how do I make a faster LAN network, which is important, and it has a profound impact on node and local performance, right? And it's part of a larger system, but you also now start to see things like WAN behavior dominate this discussion. And again, back to that checkpointing thing, right? If we could make approaches to training that really were much more resilient to node failure and needed less checkpointing and less data exchange, you could get a profound either improvement in performance or decrease in cost. Again, you go to the teams that are responsible for WAN and you start your sentence with the word petabit, right? And it is a challenge, right? It's not like the optics are getting that much faster each year, but here we are.
Right. Okay. Another question from the community. This is from Kyle Sorensen, and his question is: how important do you think it is to determine if a node is at risk before failure during training jobs? That's something that you've looked into, George?
Oh, sure. I mean, being able to predict node failure from, precursor signals, right? Obviously, the best thing you can do is you typically have redundancy even at the rack level, right? And so you'd say, well, if we've got a bunch of nodes in that rack and whatever, I'll make up a number, right? Suppose there's 50 nodes in a rack and 2 of them are exhibiting signs that tell us that statistically they are at increased rate of a risk of failure. You would run that training iteration on the other 48, and you would dispatch somebody to go and perform the appropriate service on the 2. So hugely valuable, right? Like anything that reduces actual node failure during participation on a training run is fair game. And a failure prevented, which translates into a lower overall experienced rate of node failure, is super valuable. A lot of node failures are not showing precursor signs; they just happen, and that may just be because we don't have good enough telemetry, right? I'll pick one example, right? Maybe you have heat sink bonding issues, and you've got heat sinks that gradually start to work themselves loose over many, hot cold cycles. And what you need is noticing that parts of the chip are starting to have temperature variations, or, the HBM is starting to show that it's hot, right? All of those things are fair game here. Anything that prevents a node from failing while it's participating is highly valuable.
Okay. One more question from me, and this is the storage sort of architecture and the storage hierarchy. Is like, storage in HPC has a special place, but when we're talking about a gigawatt scale infrastructure, how does one even go about sort of architecting that? What are your hierarchies? What do they look like? Especially when you're trying to plan it for a training workload.
Right. I mean, back to my earlier comment about modeling, the thing to remember is no one actually cares about storage, right? They care about system throughput for the
Right.
application. And right, tape. That's right. Well, with current HDD supply chain challenges, maybe we will see a resurgence of tape, but probably not for HPC. No, it's very much a systems problem, right? If you have faster storage or more local storage, then you get better performance out of the nodes that are attached to it. But you eventually have some kind of fixed capital budget that you're operating against. So that means you have either fewer nodes or you have less network or something else. And so being able to model the impact of storage on the performance of the node for training workloads, for example, is absolutely critical. And also, and I can't emphasize this enough, right? The nodes are going to be doing frontline training for maybe a year to 18 months of their life. They last for 6 years, really, right? If you spend a lot of money to optimize performance for that first year and a half, and then it is E&O for the other 4.5 years of this, what you've effectively done is you've increased your total costs and therefore decreased the total capacity that you can afford. And so this longitudinal view of cost is really, really important if you actually want to have the most competitive offering. And whoever you are, including Google, right? Your competition is obviously making their own analysis and plans for these things. And so if you want to be the best at it, you have to worry about your capital budget application over time and optimize for the whole life cycle of these servers.
Okay. All right. Another question from the audience. So what kind of PUEs or the efficiencies, do you get at the gigawatt scale versus, say, the 100 megawatt scale, and specifically for AI ML workloads?
In general, PUE gets better with scale for a few reasons. The first, of course, is that what you're actually interested in is not peak PUE, but average PUE, right? I have a gigawatt scale deployment, no matter how it's charted out across the geography, right? I'm interested in knowing how many watts I have to consume to get the necessary chip power to do my training application or my thing, right? Peak PUE is interesting because it affects data center design, but average PUE is interesting because it affects costs, right? That is the power that you will draw. And so generally what we see is that with increasing scale, you get better PUE. For all the normal reasons, right? Your redundant capacity is amortized over a larger fixed base, right? You have, technologies that let you do free cooling, whether that be free air cooling or, higher water temperature or et cetera, et cetera, et cetera. More engineering becomes economically viable as the scales get bigger. And so you can start to come up with novel or innovative solutions. But in general, what I expect with AI is two things. Number one, obviously, we've switched from air cooling to liquid to the rack, which increases the cost of the rack, but actually should decrease the cost of the data center because you're not sort of doing your heat exchange through two different inefficient mediums. Air goes into the rack, air comes out of the rack, you grab the air, you cool it back off, you send it right. You don't have to do that anymore. Now you can send water straight to the chip and take most of the heat out that way. And that has opened the door, for example, to using higher temperatures. I mean, that's something that Google's been doing for a long time in our data center with our air temperatures, but you can use higher temperature water as well. And okay, if you've got higher temperature water, then a lot more parts of the world, you can get free cooling. Great. So I would generally expect to see that PUE will gradually improve with these large-scale AI deployments.
Okay. One more question from Wesleyan Church, and this one is more about the whole supply chain. So the question is, how do you approach supply chain for something like this, where you're operating at such a large scale? And is there competition for resources?
So sorry, that wasn't laughing at the question. Just turns out there is competition for resources, and it is profound. I think I'll phrase it this way: there is such an element of competition for resources at all levels, from data center equipment to networking equipment to access to power to chips and packaging and so on. It's actually become a normal part of supply chain planning to do essentially, competitive analysis and competitive planning. And I know that there's obviously a fair bit of concern at multiple levels, both inside and outside of private industry, around supply chain and its impact on the ability to continue to grow and sustain the kind of investments in machine learning. But it's a profound thing, right? Like, just back to my earlier point, we weren't building gigawatt scale data centers, just a few years ago at any kind of volume, and now people are talking about 10 gigawatts. I mean, they're talking about 100 gigawatts, but what they're actually planning for is large single-digit gigawatts. All of the firms that supply equipment for data centers are not prepared for this, right? And so they're all trying to make decisions about how much manufacturing capacity do they tool up, and what happens if demand levels off. Will they be stuck with overcapacity? And so then you get into forward integration with them and investments in production capacity. So yes, the supply chain bit, though it isn't central to what I talked about here, is a huge component of what actually gets done in order to make this kind of scale of capacity necessary.
Okay, and one last and somewhat related question is like, does Google build these data centers using in-house or hire contractors? And if it's the latter, how important that these contractors communicate with each other and stay connected and so on? I mean, you're talking about the scale of this problem is huge. And you're talking about manpower, which needs to be trained. So, that's a whole challenge in it of itself, right?
It is. And I think, so to answer your question, Google has parts of the data center planning, design, and construction supervision that are done in-house. Pretty much all of our actual data center construction is done by outside firms. For lots of reasons, including they tend to be local to the data center site, et cetera, et cetera. And also it's bursty, right? Like, you do a data center construction for Google and you need thousands of people for months and then not again, maybe for a while. So it's much better to engage other firms. I think it's a competitive situation out there right now, right, in practice. And so I don't see firms doing a lot of talking to each other. Everybody is looking for their own competitive advantage. At the same time, you have a lot of best practices for the industry that end up getting propagated because there's the same design being stamped out, right? Whether it's Google or Amazon or Microsoft, et cetera. We tend to develop designs iteratively, and then we'll stamp out a bunch of instances of that design. And so the industry does catch on to, here's the designs that we've got, here's the designs that are coming.
Okay. All right. Well, thank you very much.
Fresh out of time and must run.